trains go by, and here to talk to you about mechanism independence and commons. So, hi, I'm Joe Corneli, and this is my short presentation for WoW 5. I'm talking about mechanism independence and the idea of commons and what these things have to do with each other. So, following on Deleuze's work, DeLanda contends that there are real but abstract mechanism-independent universal singularities that participate in the ontology of objects or assemblages. This is useful for us when we think about patterns, which exhibit a degree of generality, or they wouldn't be patterns. Generality may be restricted in some cases. For example, we might have pattern languages for programming, and generality may be broader in other cases. So what does this actually mean? Well, so I'm looking at these trains going by. I'm going to get on one of them at some point. I want to get into London, and the trains are available to everybody, but they're not really free. I mean, I had to buy a ticket to get on. You need to buy a ticket to ride these trains. So the idea of a commons as something that everyone has access to is quite clear. How are we going to build these commonses or common spaces? Well, that's perhaps a little less clear, and what does it mean to actually be a commons is yet another question. So I think it would be useful to take an example. So the example is mathematics that I'm very familiar with. So mathematics is something that we really all have access to as long as we can get to a university library, or maybe we go to state-run schools, and we can study. So mathematics is such as it exists is a common resource. Now, furthermore, the history of mathematics is something that's been worked out by people, right? They talk to each other, they work things out on scratch paper, maybe they build physical models that they use to test some mathematical notions like Galileo did, and vice versa. You can describe physics using mathematics. These days, of course, we have computers, and we can do certain things with computers that you couldn't do just with pen and paper, like large-scale computational simulations of things like the weather, or logistic networks. You can simulate what goes where. You could look at some data about who sold what to who, and so forth. And another thing you can do is build great websites, like Wikipedia or Planet Math is one that I've been involved with over the years, which is a peer-produced mathematics website. Now, if you want to learn mathematics, it doesn't really matter if you're learning it from a computer or from a textbook or from a teacher, in the sense that in the end it's the same mathematics. Now, one of those could be more effective as a learning methodology than another, just like getting into London by train is great, expedited right into the heart of the city. If I wanted to go by stagecoach, it would be a little bit slower and also more awkward because the stagecoaches aren't available now. So anyway, that all just goes to show you can get to the same result in different ways, and that's what I mean in a way when I say pattern. And the other aspect of that that's interesting is when you look at something that's a pattern, there's some commonality to it, okay? So Manuel DeLanda talks about mechanism independence, and that's in a way when I say pattern, again, this idea that it doesn't really matter how the pattern is implemented as long as we see the same pattern. So people want to get from here to there, that's a pattern. People find ways to enclose commons, resources, that's another pattern. You can have state monopolies, that's another pattern, and so on and so forth. Differential equations describe different kinds of patterns. So fair enough. And how can we use this stuff? Well, we're interested in systems where there are humans in the loop, okay? So we're not just physicists describing that kind of pattern. And we're not necessarily interested in the most specialized humans, so architects or computer programmers or doctors, although, of course, I suppose we're in favor of these people existing and running their own lives and thriving in their own way, but we're really talking about something that's a bit more general. So, humans in the context of being humans rather than being professionals, and how do they work together? How do they live? Of course, we can be inspired by the work that's gone on in architecture, where Christopher Alexander came up with this pattern language idea, and he said, well, if you want to design a house, don't start with the house, start with the bioregion, design the city, and look at how people in the house interrelate with each other and how they relate with their neighbors and so on. So here I am in the nearby Milton Keynes, which is a new city which I can almost guarantee you was designed with no Christopher Alexander ideas involved. However, it was built kind of from a top-down design standpoint. So the real question for Christopher Alexander is, how can you build cities that are, or living situations that feel alive? He talks about this sense of life. Whether it's a nice neighborhood or a village that's kind of grown organically, or something a bit more artificial like Milton Keynes, we could ask a different question, which is, how does order emerge out of disorder in the first place? What are the inconsistencies and splittings that allow the edifice of order to maintain itself? And that's a quote from Slavoj Žižek. So let's think again about the case of mathematics on computers. So, in the case of mathematical thinking, humans are in contact with a rich, phenomenal world. So we can do natural experiments, dropping balls off of leaning towers and so forth. Computers don't have that ability. They only really do what they're programmed to do. So what would a minimum mathematical model of minimum model of mathematical creativity be? It should include agents and phenomena. So what does that mean? Well, you might model someone who's using a mathematics website as an agent, and you could model what they learn or encounter, including their interactions with other agents, as phenomena. So basically, having agents exist simultaneously as part of each other's phenomenal worlds is what we call sociality. So we can describe things like that in simple ways using philosophical or computational models, but if we really want to go further, in the specific case of mathematics, we would want to talk about proofs and subproofs and proof steps and heuristics and social heuristics. And we'd all want to make that very concrete in the case of, specific mathematical operations like carrying a digit or factoring a polynomial or finding a root or designing a mechanical structure. And you could find different kinds of mathematical cultures or knowledge bases that would suggest different approaches, and would even suggest different kinds of problems that are relevant to solve. Like, some may say building bridges is the thing to work on. Others may say, no, we want to study quarks. So that's mathematics, and we can take mathematics as an inspiring example and look at a more general case of patterns. Okay, so mathematics studies patterns, but again, I was saying we're interested in social patterns. So here, progress means formulating and describing some kind of new or useful pattern. So patterns and pattern languages could be viewed in this way as a kind of dialectics, where we would negotiate with each other, okay, this is a interesting pattern, this kind of thing is important to us. Say, for example, we want to foster newcomers in our organization. So we say, okay, not only do we want to foster newcomers, every organization is going to have newcomers. That's a pattern. So let's study what it means to have newcomers. And again, getting back to that idea of mechanism independence, we can come up with a kind of somewhat abstract formulation of patterns. We say, well, there needs to be an idea and a context in which it's meaningful. There needs to be some kind of problem to solve. There needs to be some kind of solution. There needs to be some reason that it's a problem in the sense what might go wrong. It's not just a straightforward operation that you do without any problems. And, once you're done, the world continues. There's some kind of next step. So that's a fairly general and rather abstract formulation of what it would mean to describe a pattern. I gave one example, which was a newcomer. Another example that we've used in the Peeragogy project is the roadmap. So we would say, well, every project is going to need a plan, and so on. So now you might say, well, if you build up a large catalog of this kind of patterns, maybe we could use them as a sort of calculus, like collection of mathematical patterns that we would do. And in fact, maybe we could even mathematicize these human problems and describe them in a much simpler framework, just in terms of an initial state, an end state, and the forces that are in action during the course of this system progress. And of course, some of those forces may be agential. They may have to do with the agent's volition. They may be physical, like space, time, distance, and so forth. And so we need a mix of humanistic and physics-inspired models to really make much progress. And I guess, basically to draw it to a close, the abstract models that we're talking about need to be instantiated in very specific and particular mechanisms, like a specific pattern language describing a specific kind of force acting or set of actors or problems in order to be useful for anything. So that doesn't defeat the idea of mechanism independence, because we may say, okay, patterns are, first of all, that's, as I've explained, that's what makes something a pattern, is it's got a degree of generality. But also, quite usefully, if we agree to some extent about how we're going to describe these patterns, then we can describe patterns as has been done for architects and computer programmers. These things can interact with each other to some degree, and these different groups can negotiate. So that's one of the things that's very useful about these pattern languages, as we can start to look at the higher level patterns. How do the patterns themselves get communicated, changed, and negotiated?